Let's let A be an m by n matrix. The row space of A is the subspace of n space spanned by the row vectors of A. So we're defining row space, and the row space of A is the subspace of n space spanned by the row vectors of A. The column space of A is the subspace of Rn spanned by the column vectors of A. So another important concept is column space. So the column space of A is the subspace of R to the n space spanned by the column vectors of A. Let's look at an example. Let's let A be the matrix 1, negative 1, 2, 0, 1, 0. So A is the 2 by 3 matrix 1, negative 1, 2, 0, 1, 0. The row space of A is the set of all vectors U such that U is equal to C1, 1, negative 1, 2, plus C2, 0, 1, 0. So the row space of A is the set of all vectors U such that U is a combination of the row vectors. U is a linear combination of the row vectors. So the row vectors will span the row space of A. The row vectors will span the row space of A. So that means the row vectors will form a linear combination of the set of all vectors in the row space. Well, this would be, if you look at this, would be C1, negative C1, 2C1, 0, C2, 0. So that would be C1 plus 0, which is C1, a negative C1 plus C2, and then 2C2 plus 0, which is just 2C2. Well, if we write it in terms of parameters S and T, the row space of the set is that C1 be S and C2 be T, be S, a negative S plus T, 2T, where S and T are any real numbers. So here would be the row space of matrix A. Again, you take the rows of A, do the linear combinations, and you get the row space. If A is row equivalent to B, then the row space of A is equal to the row space of B. Now remember, A is row equivalent to B if A can be transformed into B by the elementary row operations, which means you can interchange any two rows. You can multiply a row by constant. You can multiply a row by constant and add it to another row. So using those three row operations, if I can transform A into B, then A is row equivalent to B. Now if A and B are row equivalent, then the row space of A is equal to the row space of B. We have another theorem. If A is row equivalent to B and B is in row echelon form, then the non-zero row vectors of B form a basis for the row space of A. So if A is row equivalent to B and B is in row echelon form, then the non-zero row vectors of B form a basis for the row space of A. So this theorem really gives us the set of steps that we would need to do to find the basis for the row space of A. So if A is any vector, then what I would first of all is to reduce A to row echelon form and get vector B. By using the elementary row operations, I would know that B is row equivalent to A. Then I can pick the non-zero row vectors of B as the basis for A. So just take A, put it in row echelon form. The non-zero row vectors form the basis for the row space of A. Let's look at an example. But first I'm going to give you a couple more definitions and theorems so we can look at them all at one time in the example. The row space and column space of A have the same dimension. The row space and the column space of A have the same dimension. The dimension of the row space of A is called the rank of A, and it's denoted by rank A. Now we're ready for the example. We're given matrix A, which is equal to the matrix 2, negative 3, 1, 5, 10, 6, 8, negative 7, 5. Find the basis for the row space. Okay, step 1 in finding the basis for the row space would be to write A in row echelon form. In other words, what we want to do is to row reduce A. Well, we could do that starting row reducing. I could multiply row 1 by negative 4, add to row 3, multiply row 1 by a negative 2.5, add to row 2 to create the zeros here, and go through the elementary row operations. I assume that you're already fairly good with the elementary row operations, so in order to save time, I suggest that you use derive to do your work. So you can go to derive, and you can author your matrix. So this is matrix A that we've authored. Two, negative 3, 1, 5, 10, 6, 8, negative 7, 5. Which is the same matrix that we had there. Now, what I'm going, once I author the matrix, then I'm going in and I'm going to have derive to row reduce this. Derive has the command, so I can go to author expressions and I can type in row reduce number 1. So what I enter is row underline reduce parentheses number 1. So go ahead and author your matrix, and then you can author expression and put in row reduce number 1. So you can see this is what we're doing here. We have the row reduce number 1, and there is your matrix from number 1, and we get 1, 0, 4/5, 0, 1, 1/5, 0, 0, 0. So now here is the second step. So first, write A in row echelon form. Step 2 is the non-zero rows form a basis. So the non-zero rows would be 1, 0, 4/5, 0, 1, 1/5. So there's your basis. Now you're probably going to see it written as 5, 0, 4, 0, 5, 1. Because remember, with the basis, if it's a basis, then the linear combination, all the vectors in the base, will give all the vectors in the set that it's spanning. So if it's spanning, then it would be the linear combinations. For linear combinations, you multiply by a constant. So by multiplying by the 5, that's just going to change the constant, which could be whatever it takes anyway. So normally speaking, you will see the answers written in the whole number form rather than fraction, but it really doesn't make any difference. Now find the basis for the column space. Okay, well, one method is to find A transpose and then get the basis for A transpose. Well, that's probably the simplest thing to do, especially if you're using derive, and see why it would be logical. If to find A transpose, that means I'm interchanging rows and columns. So what was the row now becomes the column. What was the column now becomes the row. So what was the column now becomes the row. And get the basis for A transpose is row space. I didn't finish that. So find A transpose, get the basis for A transpose row space. Because if we A transpose, what was the columns are now the rows. So if I get the basis for the row space of the transpose, then I've got the basis for the column space of the matrix. Well, let's go back to derive, and I go back and I put number 1 transpose. When I do number 1 transpose, I get 2, 5, 8, negative 3, 10, negative 7, 1, 6, 5. So what was the row becomes a column. What was the column becomes a row. So now I'm going to get the row space, or the basis for the row space of this matrix. So I'll row reduce. And I see that one basis is going to be 1, 0, 23 sevenths, 0, 1, 2 sevenths. That's one basis. I'd probably write it as 7, 0, 23, 0, 7, 2. So we have the basis for the column space. Again, the theory, take the transpose, so the columns became the rows. Find the basis for the new row space will be the basis for the original column space. Now there is another way that you can do it. This way is probably a little less clear, but another way that you can get the column space is to go to where you row reduced the original matrix. Look at your rows that begin with a 1, and then go back to your original matrix, and that will tell you the columns to pick for your column space. So I need to pick columns 1 and 2. Because row 1 starts with a 1, row 2 starts with a 1, or where you have the 1s on there. Now, of course, this one we don't pick, so I'll pick column 1 and column 2. So another basis for the column space, I'll say A sub C for the column space, another basis for that would be 2, 5, 8, negative 3, 10, negative 7. So once this tells me which columns to use, 1 and 2, I go back to my original matrix to pick those two columns. I suggest that you do the transpose method, at least initially. Let's give the rank of the matrix. Well, the rank of the matrix is going to be the dimensions of the row space. Well, the dimensions would be the number of elements in the basis. So if we go back to the row space, 5, 0, 4, 0, 5, 1, we had 2 vectors in the basis, so therefore the dimensions of the basis is 2. So the rank of the matrix is 2. So we say the rank of A is 2. Now recall that we said the rank of the row space would be the same as the rank of the column space. Well, the row space had 2 vectors. The column space had 2 vectors. So we see the rank of the row space is the same as the rank of the column space. So that would be the rank of the matrix. We can use today's work to find the basis for a set written in vector form. So let's find the basis for the set of vectors S is equal to 6, -3, 6, 34, 3, -2, 3, 19, 8, 3, -9, 6, -2, 0, 6, -5. Well, to find the basis for it, what I can do is write it in matrix form and just use these as the rows of the matrix. So 6, -3, 6, 34, 3, -2, 3, 19, 8, 3, -9, 6, -2, 0, 6, -5. Find the basis of the row space of A. So I can write it, this set, matrix form A, and then find the basis of the row space of A. And that will be a basis for set S. Well, to find the basis for A, I need to row reduce it and take the non-zero rows. So we've authored matrix A and we row reduce A. Once we row reduce A, we get the identity matrix. So the basis B is going to be the identity matrix, or the set of vectors for these rows. 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. So the basis for the row space of A will be the non-zero rows. So therefore, the basis for set S is going to be the non-zero rows of my row reduced matrix, which will be the same set.